Hello friends, welcome back to the tetrahedron chemistry classes. As I have already uploaded a video regarding the information about the June 2022 examination registration. Okay, so since the examination is there on the corner, so today I am going to continue with my chemistry lectures in the tetrahedron chemistry classes, and today I am going to discuss the series of the spectral problems. And so far I have solved CSIR NET June CSIR NET spectroscopy problem starting from 2011 to 2014, right? So now today I am going to solve the CSIR NET problems for year 2015 examination, where I will discuss 11 different problems in the pretty much details. Okay, so my first problem is from the June 2015 examination, and the problem is quite simple here. The compound that shows sharp bands at 33 centimeter 100 inverse and 2150 100 centimeter inverse in the IR spectrum, and you have been given the 4 options. Okay, so this compound this question tests your knowledge about the IUPAC nomenclature, how to draw the structures, as well as for the IR spectroscopy. So how we can solve that? To solve this question, I have to draw the structures of different compounds given in the question. So this is butane 1, so I can put triple bond here. This is your CH, okay, and this is your CH2, and this is your CH3. So this is your compound A, and compound B is your butane 2, so C, triple bond C, CH3 here and CH3 here, okay. And then you are having your compound C, which is your butyronitride, and since it is the butyronitride, that means cyanide group is there, so you can write CH3, CH2, CN. Okay, so intentionally I have written in the form of the triple bond this molecule. And last option is your butylamine, so CH3, CH2 again, this is CH2 and NH2. So how we can solve the problem? So first of all, what you can do, you can look for the value given. The value given is 3300 centimeter inverse, and you know this 3300 centimeter inverse in this, or in the compound, you can see here there is no OH group, so there is no question of looking the compound which is having the OH group. You have to look for the CH stretching. So if you know a little bit of the IR spectroscopy, you know this CH3 stretch, when you have the CH3 methyl group and you are looking for the CH3 stretch, so it comes around 2900 centimeter inverse, okay. And if you are looking for the CH3 CH stretch for the double bond, so it will come around here 3100, okay, centimeter inverse. And if the compound is the triply bonded, then your CH stretch would be greater than 3300 centimeter inverse. So first thing you have to look for the CH, whether this CH is present in the molecule or not. So here in that case, you can see if you go for the option 1, in option 1 this CH is present, so this could be the answer. But this option B is not having any CH, so you can immediately discard this particular option. So this cannot be your answer. And third question, third option itself is not having any CH stretch, and moreover it is having the CN stretch, and you know this cyanide in the IR spectrum appears somewhere around 2250 2000 to 250 centimeter inverse, but this value is not given. It is 2150, right? It is 100 less than this one, and moreover it is also not having the CH stretch, so this could not be your answer. So what you can do, you can strike out your option C also. Now go for the option D. This option D is also not having any CH stretch. When CH stretch is not there, and moreover this amino group is there, NH2 group, and you know this NH2 group in the IR spectrum, it resonates around the 1600 centimeter inverse. So this 1600 centimeter inverse is not there in the question. So you can immediately strike out option D also. It is looking that your option A is the correct option. So Why it is correct option? Because it is having the CH stretch which would resonate around this value 30 and 3300 centimeter inverse, and moreover you are having carbon triple bond carbon stretch, and for this carbon triple bond carbon stretch you have to look for this value 2150 centimeter inverse. So option A is the correct answer. This was the pretty straightforward question, but you should, for to solve such kind of the question, basically it's a memory based question, so you should memorize the values, the important values in the of the functional group in the IR spectrum. Now moving to the next question, what it says. My next question is again you can see here, it is from June 2015 examination. The proton NMR spectrum of a dilute solution of a mixture of acetone and DCM. DCM is here dichloromethane in CdCl3. CdCl3 is the deuterated solvent which we generally use in the NMR spectrum during the recording of the NMR spectrum. And this NMR spectrum shows two singlets, that means two single peaks of the intensity 1:1. What would be the molar ratio of acetone to dichloromethane in the solution? And you have been given four options, and you have to solve this particular question. This question is again a very straightforward and a very simple question. How we can solve this particular question? For this, guys, you should know the structure. You should know the structure of this acetone. This is CH3, COCH3. This is your acetone. Then you are having your dichloromethane, which is CH2, Cl2. It is dichloromethane. Both are the solvents. Both are the organic solvents, basically. How many protons are there in the acetone? 6 protons are there. Okay, that means 6 hydrogens are there, and in that case you are having the 2 hydrogens. So if you take the mixture of this and if you take the NMR of this one, so this will give you the intensity of acetone will give you the intensity of the 6, and this will give you the intensity of your 2. But in the question itself it is given that we are getting this intensity pattern of 1:1. Okay, we are not getting the pattern of the 6:2, or rather you can say the 3:1. Okay, so how it is possible to get this kind of pattern? Say for example, here you have to actually, what you have to do, you have to make these protons, these number of protons to 6. When you make this these protons of your dichloromethane 6, then there would be the intensity of the 6:6. Okay, and when you have the intensity of the 6:6, then it will give you the molar ratio. So to get this particular molar ratio, what you will do, you will multiply that dichloromethane with 3, and you will multiply this with the 1. Okay, so here the intensity is what? 1:2. So molar ratio is what? 1:3. That means 1 mole of the acetone and 3 moles of the CH2Cl2 would be there in order to give the intensity pattern of the 1:1. So your correct answer in that case is your 1:3. That is option B. Okay, this is the correct option. Now moving to the next problem, what it says that my next problem says that intense band generally observed for a carbonyl group in the IR spectrum is due to. Okay, it's a theoretical question, and for this kind of the question actually you have to knowledge about the say selection rules and the theory of the different spectroscopic techniques. Okay, and what are the options? Large force constant. So large force constant is nothing to do with the intensity of the band. Okay, so generally large force constant means your resonating frequency. Okay, it is not related to the intensity, but it is related to the frequency. So this cannot be your answer. So what you can do, you can immediately strike out this one. And then what is your option? Second, small force constant. Again you can strike out this one. There is nothing to do with the force constant. And then your option C, no change in the dipole moment of the carbonyl stretching frequency. See guys, this cannot be the answer, because for a molecule to be IR active, it is the necessary condition that your molecule must be a polar molecule, and if the molecule is polar and you actually shine IR light on this one or light on this one, then its amplitude increases, and when the amplitude increases, dipole moment also changes, right? So no change in the dipole moment cannot be the answer. Again, third option is wrong. So what left with the fourth option, automatically you can mark this option as correct option. large change in the dipole moment of your CO group. So this option D is the correct answer in that case. Okay, now moving to the next problem, what it says that my next problem is an organic compound shows the following spectral data. IR, see in the IR spectrum you are getting this 1680 centimeter inverse of the peak, which is I think the region of the carbonyl group. Okay. You know this around 1700 your carbonyl resonates, and depending upon the type of the carbonyl, whether it is acid, it is ester, it is anhydride, it is aldehyde, it can shift from your 1700 to 1800, and it can come down from 1700 to 1600. So basically it's a region of the carbonyl group. So you have to look for the carbonyl group in the molecule. So later we will see how we can solve this one. And the proton NMR spectrum says that you are having 7.66 multiplate, one proton multiplate at this chemical shift value, and at this chemical shift, that is 7.60, again you are getting a multiplate of your one proton, and then at 7.10 you are again getting the multiplate, that is of one proton, and finally you are getting a triplet. This triplet you are getting, this singlet you are getting, not triplet, this singlet of the 3 proton. Basically it's a methyl group. Okay, three hydrogens are possible in the methyl, and it is a singlet, so it is actually your methyl group. Okay, and then you are having the carbon 13 NMR 190. Again it is suggesting that it is the presence of the carbonyl group. Okay, so 180 to 210, it is the position of the carbonyl group. So carbonyl group must be there in the molecule. And 144, 134, 32, and all these things. And finally, see in this question, generally mass spectral data is not given in the CSIR NET question, right? But in that case you have been given that 126 m by z value. This is electron impact ionization, and it is giving you a molecular ion peak. M positive stands for the molecular ion peak, and it is also having the intensity of the 100%. That means it is also the base peak. So molecular ion peak and base peak is same in that case, and it is around 120, not around, it is at 126 m by z value. And after that you are getting the this value 128, and 128, that means if you add 2, if you add the 2 on this 126, you will get the 128. That means m plus 2 peak you are getting, and the intensity of this m plus 2 peak is your 4.9%, right? So this question actually is quite an important question, and you will learn lot of things while solving in this for solving this particular problem. So here how we can approach. See, first of all you will see this thing. Let me shift it over there. Okay. See guys, all this compound is having the molecular weight of 126. This is also, B is also having the 126 molecular weight, C and D. So all compounds are having the same molecular weight, that means 126. That means all will give you the molecular ion peak, a very prominent molecular ion peak. Okay, but this compound is actually giving you m plus 2 peak. So if you have seen my previous video on the mass spectrometry, then you will be straightforward jump into the conclusion that m plus 2 peak is very common in case of the chlorinated compound. It is very common in case of the compound which contains the sulfur. So basically this compound actually contain this this molecule, right, should contain the sulfur in it. So option A, you can see the sulfur is not there. Option A, sulfur is not there, so you can easily strike out this sulfur from here. So this cannot be your answer. You can easily strike out this option A. This cannot be your answer because it is not having the sulfur. And one more thing you can do, what you can do, you can delete this AC, okay, and okay, there is no need to delete this AC. So you can straightforward strike out this one. Similarly, the option C is also not having any kind of the sulfur present in it, so you can strike out option C also. So what you left with the option B and the option C. So out of these two, whether option B or option C, out of these two, one would be correct. Okay, B or D, sorry, option from option B and D. Now we have to look the things actually. So first of all, I'm giving you the details how you can think about the isotopic abundance. Say basically your sulfur is having sulfur 32 and you are having sulfur 33 and you are also having sulfur 34 and finally you are having the sulfur 36. Okay, and if you take the isotopic abundance, it is very rich, 95%. It is quite a small, it is present in the quite a small amount, 0.75%, so it will not affect your mass spectrum drastically. And then your this sulfur 34 is having 4.4%. Okay, and this is again 0.02%, right? So again it is very low, so you can strike out this one. And what you can do, you can focus only these two, this and this, and you can see the 4.4 intensity is there. It clearly indicates that this M+2 peak is due to the presence of the sulfur. So that's why you have discarded the option A and the option C based on the presence or the absence of the sulfur. Now again we can move further. What you can do here, what is given here, see in the IR spectrum you are having 1600, what you can see here 1680. This 1680 basically it is due to the presence of the carbon double bond oxygen. It is due to the carbonyl group, and this carbonyl group is also presence of this carbonyl group is also indicated by this 190 value. Okay, that means your molecule is also having the carbonyl group. So when your molecule is having the carbonyl group, so you can straightforward see this option, this is not having any carbonyl group. This is carbon single bond oxygen, right? Carbon single bond oxygen resonates around 1100 centimeter inverse in the IR spectrum, which is not there, but this carbonyl is there, which is at 1680. So you can strike out this B also. So straightforward you can write your option D is the correct answer. Okay, and apart from this you can do lot of exercise in order to solve the structure. So what I can do, I can try to solve this question, this option D, based on the other spectral data which I've given. So I am deleting all these things. I don't require these things, these options. I don't require these options. Fast, quickly. Okay, now here you can see, if you want to understand the NMR spectrum for this one, so this is your sulfur, this is your sulfur, this, right, and this here you can see is this one. So this is your CH3, and these this CH3 basically appears at the singlet, and since it is attached with the carbonyl group, you know, it's an electron withdrawing group, so it will shift this chemical shift of CH3 little downfield, so it will resonate around 2.50 ppm. So it's a singlet of the 3 proton. Okay, and it is given here. Okay, and if you see the carbon NMR spectrum for this one, so this carbonyl resonates around 190 ppm. I think there is no problem in that. And then you are having the hydrogen here, you are having the hydrogen here, you are having the hydrogen here. Okay, so what you can do here in that case, this hydrogen can couple with this ortho hydrogen and it will produce a doublet, just like that. It will give you a doublet, and that after this it can also couple with this meta position with this here. Okay, this one, right? So this doublet will give you a doublet here. So it's a kind of doublet of doublet. It's a kind of a doublet of doublet, which is nothing but a multiplet, right? So for this hydrogen you are getting the multiplet. Same is true for this one. This will couple with this one, and this will couple with this one. This will also give you the multiplet. And this hydrogen will couple with this one, and this will also couple with this hydrogen will couple with sorry, I made a mistake. So this hydrogen also is also coupled with this one and then this one. So all will give you the multiplet. All these hydrogens will give you the multiplet. Okay, and it is there in the question itself. You see here. You see here. This is 7.66 multiplet, 7.60 multiplet, 7.10 multiplet. Now you can imagine that this 7.66 is a very large value compared to other two values. So it should be downfield. That means this hydrogen must be near to the electron withdrawing group. So this hydrogen is near to this electron withdrawing group. So this value, right, this hydrogen is basically your 7.66 multiplet, one hydrogen. So this is how you can solve this particular problem. See, if you do the practice, then you will be able to solve the questions by your own, right? But this will require a lot of practice to solve the spectroscopy question, lots of concept and all these things. Okay. Now moving to the next problem, what it says that my next problem is again from the June 2015 examination, and it is a kind of a numerical. The nuclear G factor of the proton and the nitrogen 1H and the 14H are 5.6 and 0.40 respectively. If the magnetic field in the NMR spectrometer is set such that the proton resonates at 700 megahertz, the proton nucleus would resonate at, you have been given 4 options. So you will we will see how we can solve this particular question. So there are various ways. See, there are ways to solve this particular question, but obviously you would prefer that path which is actually which saves your time. So I am giving you the option here. Basically the resonating frequency omega is directly proportional to the nuclear G factor. If you know this thing, then it would be very easy for one. So you have been given two kind of the nuclei, 1H and 14N, right? So for this you can write this particular equation. Omega 1 equals to G1, and for this you can write omega 2 equals to G2, right? Omega 2 equals to G2. And what you can do, you can say if this is the equation number 1, this is the equation number 2, what you can do, you can divide equation 1 with equation 2. So you will get omega 1 divided by omega 2 equals to G1 divided by G2. So when you have this thing, omega 1, that means your hydrogen, and hydrogen resonating frequency is given here. It is resonate. See, you hear, if the magnetic field of NMR spectrometry is such that the proton resonates at 700 megahertz. Okay, so omega is given for this one, or resonating frequency is given for this one. So you can straightforward write 700 here. 700 megahertz I am writing. Okay, and you have to calculate for the nitrogen. That means omega 2 you have to calculate. And here you can see it is what, 5.6 divided by 0.40. This data is given. This is the you can see this 5.6 is the nuclear G factor for the proton, and 0.40 is the nuclear G factor for this nitrogen, right? And if you solve this particular equation, so I have already solved it. So if you solve this one, so omega 2 would be equal to 700 megahertz multiplied by 0.40 divided by 5.6. Okay, and when you solve this equation, you will get the 50 megahertz. Answer is the 50 megahertz. So your correct option is the option number D. So here, see, if you have the little confusion about this particular problem, so I can give you a little detail here, which is from the part of the physical spectroscopy. So what physical spectroscopy says, that I am giving you the detail here. See, basically the resonating frequency omega is equals to E upon 2m. This is nuclear G factor multiplied by the B0. You know this E is constant, 2 is constant, M is the constant, and B0 is the constant magnetic field, static magnetic field which you have applied. It simply says that this omega is directly proportional to the G. Okay, so this is how you can write. Or if you want to derive the equation also, then you can derive the equation by your own also. Okay, So now moving to the next problem, what it says. Okay, now next problem. Okay, see guys, this problem is the quite tricky problem. So guys, you can see what this problem says. This problem says that the structure of the compound that matches the proton NMR spectrum data given below. So you have been given this proton NMR data and you have been given 4 compound, and you have to identify which compound actually corresponding to this particular data. So what it is given here, at 7.75 you are getting a doublet of doublet, which is having the coupling constant of 8.8 and 2.4 hertz. Obviously when it is a doublet of doublet, that means you will have the two coupling constant. First is 8.8 and after that the little one 2.4, and this doublet of doublet is due to the one proton only. Okay, and since this is 7.75, it is also already indicated that the benzene molecule is there. And next you are getting the at 7.5 you are getting a doublet only, which is having the 2.8 hertz coupling constant of the 2.4 hertz corresponding to the one proton. Third is 6.70, a doublet, and again 8.8, right, and then 6.50, a broad singlet you are getting, which is corresponding to the two protons. So guys, this actually is giving you the lot of information. Broad peak, broad peak in case of the NH in case of the NH, when NH resonates, it gives the diffuse peak. Okay, so this, and it is corresponding to the two protons. So you have to look for the answer which is having the two hydrogens attached to it. So this molecule is having two hydrogens. This A could be the answer. This B, this is also having the NH2. This could also be your answer. Option third is not having NH2. See guys, this option is not having NH2. So what you can do, you can immediately strike out this option. So I am striking out this option. So option C cannot be your answer because it is not having the NH2. And one more important data, on one more important thing which you can see here, two MEs are there. Okay, what is the meaning of the two MEs are there? One methyl group and another methyl group. That means one singlet for this methyl, one singlet for this methyl, one singlet for this methyl. That means your question itself having the should have the three singlets, okay, corresponding to the three protons each. But your question is having only one singlet, which is corresponding to the 3H proton, which is indicating only one methyl group. So option C cannot be your answer. So what I am doing, I am removing this option C from here. Okay, I have removed this. Now moving to the other options, now you can see the option D. Option D, what it says that here you can see you are getting the 3 methyl singlet at 3.80, and in the previous question you have already seen that, what you have seen that when your methyl when your this carbonyl group is having CH3 group, then in the proton NMR spectrum it will resonate around 2.50 ppm, 2.50, or say you can say 2.20. Let us check. Yes, you can see here this carbonyl group is there, it is attached with the CH3, thus the CH3 resonating as 2.50. okay, so when it is resonating at 2.50, so here you can see, but it is resonating at 3.80, so and it should be 2.80. so this cannot be your answer, so you can immediately strike out option D also. So what I am doing, I am removing the option D. Now you have to look for the correct answer. See guys, why this question is quite tricky. This question, see both these compounds, compound A and compound B, they both will give you roughly the same kind of the NMR pattern. Here the chemical shift value plays a very important role. So how the chemical shift value plays a very important role, let us investigate what is happening in that case. Okay, so I am starting with this this molecule. I am starting with this one. Okay, how I will start this. So this is my benzene nucleus, this is my NO2, this is my OMe, and this is my NH2, right? Say I have started with this one. So this hydrogen is there, this hydrogen is there, and this hydrogen is there. So for simplicity, what I can do, I can mark this hydrogen as HA, I can mark this as HB, I can mark this as HC. Okay. So first of all, I'll look for the splitting pattern, how it will look like. Okay. Say I am looking for the HA. So in the ortho position of this HA, it will couple with the HB. So this is ortho coupling. This is ortho coupling, and when it is ortho coupled, it will give you a doublet. When it is ortho coupled, so you can draw like that. It is a doublet. Okay. And of course this could be your JAB. And after that you can see this position is your meta position with regard to this one. Okay. So this will couple here again. This will couple here, and this is where you see this cannot this HA when coupling with this one, right, and it will give you a doublet only. So and any other peak is not possible. See, in that case, meta position there is no hydrogen, and this is the para position. Para position is quite far, so para coupling is not there. So HA will give you a doublet if you select this one. If you select this one. Similarly, what you can do simultaneously, I can put my H here, my H here, and my H here. Okay. See, this is HA, this is HB, this is HC. So in this particular case, this hydrogen can couple with this one, producing a doublet. So you can write a doublet here. This is ortho coupling. This is ortho coupling. But at the meta position, you are also having the hydrogen, so this can also couple with this one. And when this couple with this one, it will again split into a doublet. So you will get a doublet of doublet. You will get a doublet of doublet. Okay. And for this doublet of doublet, you will have the pattern like this. Right, like that you are having the pattern. Okay. So this is producing only a doublet, and this is producing a doublet of doublet. Okay. Now you can go for this HB. HB can couple this with this one. That is ortho coupling, and this HB can also couple with this one, meta coupling. So this HB will also give you a doublet of doublet. That means you can simply write multiplet corresponding to the one proton. Multiplet corresponding to the one proton. While this one you can write doublet corresponding to the one proton. Now if you look this hydrogen HC, right, so this HC can couple only with this one. Okay, this HC can couple only with this one, and it will also give you a doublet, sorry. Okay, so it will also give you a doublet. So this is actually this molecule is not actually corresponding to the data given, because here doublet, this will give you a multiplet, right, because it will connect here and then it will connect here, right, because this will link here, this will couple here, and this will again couple here. So this should give a multiplet, but this multiplet is not there in that case, right. While in this particular case, you can very easily see a doublet here and a doublet of doublet. See, this doublet of doublet is there at 7.75, right, and it is also very close to the electron withdrawing NO2 group. And when this electron withdrawing group is there, that means it is going downfield. So this HA should be downfield, and it is quite downfield at 7.75, where doublet. And see the coupling constant. This is the ortho coupling, right? You can see here in that case. And after that, it will couple here the meta coupling. Meta coupling is quite low. This 2.4, and it is corresponding to the one proton. So for this first assignment itself, it is looking like that option B is my correct answer. Okay, so you can see up to this point you can blindly mark your option B as the correct answer, but if you want to go furthermore, you can investigate your spectra, your NMR spectrum further. So in that case, option B is the correct answer, which is giving the doublet of doublet, while rest of others are not giving the doublet of doublets. Okay, so this is how you can solve this particular problem. Okay, if you have if you have any confusion regarding this particular problem, you can inbox me, you can comment in the inbox. I will try to answer again. Okay, so this is again a very important one. Now moving to the next problem, what it says. My next problem says that correctly matched structure and the carbonyl stretching frequency set is. So you have been given these lactones, okay, cyclic esters, they are the lactones, and these lactones are having the in the PQR form you are having 3 lactones, and the X, Y, Z you are having their resonating frequencies in the IR spectrum basically. Okay, so what is the correct match in that case? So I am giving you a trick which will help you. First of all, you should remember this point: conjugation lowers the resonating frequency. The resonating frequency. Okay, this giving you the conjugation lowers the resonating frequency. And what you can do, you can immediately think here. You see here for this compound, right? I am talking about this option R. Okay, so what this option R is saying, you see, this is my carbonyl group, this is single bond, this is double bond. So this is the conjugated one. So how the conjugation goes in that case, if you want, this will come here and this will come here. Okay, and if you draw the structure for this one, so you end up with this kind of the structure like that. It would be double now, it is single bond oxygen, so it is single bond now. When it is a single bond, that means it will resonate at the lower frequency, it will require lower energy to resonate. Okay, so R should have the lowest resonating frequency, and you can see here among these three the lowest value is what? 1715. That means R must corresponding to the X, must correspond to the X. So you have to look for the answer where R is corresponding to the X. Let's say in the option A, R is corresponding to X, this could be your answer. Option B, R is corresponding to the Z, where Z is the very highest value, so this is not possible. So what you can do, you can immediately strike out option B, here. Now moving to the next problem. Here again you see R is corresponding to S, this could be your answer. Option third, R is corresponding to Y, which is the higher value, 1770, it is the higher value than 1750. So this 2 cannot be your option D cannot be your answer. What you can do, you can immediately strike out this one. It's simple. Now you left with the 2 options only, and you have to, out of these 2 options you have to go for the correct answer, which one actually will give you the exact value, right? So here in that case you see R is corresponding to the X. Now let's check what is this. See guys, this option, this, okay, this one. This carbon is sp2 carbon, okay, which carbon is electronegative, and this oxygen is also electronegative. So this will suck the electron density towards itself. When it will suck the electron density towards itself, that means this carbonyl group actually, due to this electronegativity of this oxygen, it compresses. When it compresses, so it should have the high resonating frequency. That means this Q must correspond to the 800. Q must correspond to the 1800. Sorry. So check the options where this Q is corresponding to the Z, which is 1800. So Q is corresponding to the Z. So with this assignment you can blindly mark this option A is the correct option. So this is how you can solve this particular problem. It is based on the electronegativity, it is based on the conjugation, all these things are there. Now moving to the next problem guys, what it says. Okay, the question says the number of the chemical shifts and the non-equivalent protons expected in the proton NMR spectrum of the alpha-pinene is. So alpha, you should know the structure of the alpha-pinene. I think this question, structure of the alpha-pinene was given in the examination itself, but unfortunately I forgot to draw the structure here. Not unfortunately, you should know the some of the basic organic molecule, basic natural products. This is this alpha-pinene is present in the essential oils basically. Okay, it's a monoterpene. So how the structure looks like for this alpha-pinene? A 6-membered ring having the methyl substitution over there with a double bond here, and then this is connected with here, and these are the two methyl groups. Okay, so this question, guys, seems a very important question, because this question has involved a lot of concept in it. See here, in that case you should know the diamagnetic current, in which direction it is flowing, the shielding and the de-shielding concept, right, and the topicity. See, I have made a video on the topicity of the NMR. Okay, so if you haven't seen that particular video, so here at the right top corner in the I button information bar, you can see the link. You can go through this link and learn the topicity, okay, and the NMR problems. So let's come back to this particular problem, and we can simplify this higher. We can simplify this structure. Okay, how we can draw this structure? Okay, this will not give me the correct picture. So what I am doing, I am drawing like in that manner. Say this is just like that. Okay, right, and then just like that. This is your double bond, this double bond, guys, and this double bond is having hydrogen over there. Okay, sorry, methyl over there. So you can write, you can put methyl over here, and after that you can see here this is double bond position, and here if you check here, this is double bond position 1 and 2. Second position you are having 2 methyl groups. So this is your double bond position. This is position 1, this is position 2. So this will have the 2 methyl group. So what you will do, you can put the 2 methyls over there. They are nothing but the CH3. This is also the CH3. This is also the CH3. Okay. So how many different kinds of the protons and the signals are there in that case? We can assign this. We can assign this problem. Okay. So first of all, what we will do, we will check how it goes. Say one hydrogen is here, there is no problem in that, and you see two hydrogens are here, there is no problem in that, and two hydrogens are here, again there is no problem in that, and one hydrogen is there, again there is no problem in that, and one hydrogen is there. Okay, so this structure is looking just like this. Okay, so in that case you see here this double bond is there. This is the alkene system, and if you know this is the alkene system. Okay, and these are the hydrogens in the NMR spectrometer, and you have put it the external magnetic field, and these are the magnetic line of forces. Okay, so when hydrogens are outside the ring, outside this double bond, so they are actually de-shielded. They are de-shielded. So the same concept you can apply here. This ring is there, and the magnetic line of forces will come like that. So this, you see, this is in the direction of this one. So this methyl group is the de-shielded one, while this is not that de-shielded. Please remember, this is not de-shielded. Or what we can do, or you can think vice versa. For this you have to imagine the magnetic line of forces, or you can see this is near to this one. Okay, this is de-shielded, this is not de-shielded. That means due to this magnetic anisotropy, or this is diamagnetic shielding concept, this methyl group is de-shielded and this methyl group is the shielded. That means 2 methyl, which should give one peak in the proton NMR spectrum, but due to this double bond, right, this is de-shielded, so they are not they are no longer remain the identical methyl group, so they will give you the different peaks. Okay, so when they will give the different peaks, so what you can write, it will give you the one peak and it will give you the second peak. There is no problem in that. Okay, and after that you see it's a very important question, very important thing. This point, right, this here you can see. Okay, or rather you see this point, right, this is your chiral center. How this is the chiral center? Because this is attached with the four different groups, right? So this is hydrogen here, this carbon having 2-methyl, second group, this is having CH2, another group, okay, and this is having the CH2. So this is the chiral carbon. So what I can do, I can put the chiral mark here. And just next to the chiral carbon, if you are having another carbon, then these two hydrogens are distereotopic. These two hydrogens are distereotopic. And in the proton NMR spectrum, distereotopic hydrogens comes at the different chemical shift, while enantiotopic hydrogens gives the same chemical shift, since they are the distereotopic hydrogens, right? Or what you can do, you can go for the test ligand type of thing. What you can do, you can change this ligand and then check the configuration of this one. All these things you can do by your if you know the stereochemistry. So the point is that due to the presence of this chiral center, this carbon, which is having the two hydrogens, they are distereotopic in nature. When they are distereotopic in nature, they are different. They will give you the different peak in the proton NMR spectrum. So what I can do, I can write, say this hydrogen is hydrogen 3. I can write this hydrogen as hydrogen 4. Okay. So this I can write as hydrogen 5, and this methyl group will give you the other peak. This is your hydrogen 6, okay, and this will give you the hydrogen 7. This is your hydrogen 8. Now you left with this one, right? These two hydrogens, whether they are equivalent or not. They cannot be equivalent, right? Because this molecule is not having any plane of symmetry, right? There is no sigma plane on that. If the molecule is drawn, say for example, in case you have been given this molecule, right, like that. Forget about the double bond. So how you can draw this molecule? You can draw like that. It is a very good practice to draw these structures actually, okay, and these are the two hydrogens, right? These are the two hydrogens. Okay, so in that case, if this double bond is not there, see, and this methyl is not there, then in that case it is quite easy to say that, okay, these two hydrogens, if they are attached here, they are the identical one. But in that case there is no plane of symmetry. So these two hydrogens, again you can see this is the chiral center, and these two hydrogens are just next to the chiral center. So these two are also distereotopic. So they will give you another peak. Okay, so when they will give you the another peak. So you can write is H9, it is H10. So total 10 different kinds of hydrogens are there, and along with this 10 different chemical shifts would be there. So you can write, you can blindly mark option D as the correct option. So option D in that case is the correct option. So two methyl groups are different. The hydrogens which are connected with the two chiral centers, they are again the different one, right? So this is how you can solve this particular problem. Very important one, but you will need a lot of practice to draw such kind of the molecules in order to solve this particular problem. Now moving to the next problem, what it says. Okay, in the mass spectrum of 1,2-dichloromethane, the approximate ratio. Okay, so see guys, this problem is based on the mass spectrometry, again the isotopic abundance. Okay, and this problem in the pretty much detail I have solved in the separate lecture where I have discussed the isotopic cluster peaks. If you haven't seen that particular problem, go see, go through this I button on the top right information bar. So here is the link for this particular question where I have solved this one. Not only this particular question, these kind of questions I have solved in the pretty much detail there by approaching a different concept which is given in the, which is the concept is the expansion of the binomial expression. Okay, so I am not solving this problem right now. Now moving to the next problem, what it says that my last problem, what it says, the proton NMR frequency at 1.0 Tesla, this is the magnetic field, is 42.4 megahertz. That means your proton is resonating at 42.4 megahertz, and 1.0 is the Tesla is the magnetic field. If the gamma, that means gyromagnetic ratio or magnetogyric ratio for proton and carbon 13 are 27 into 10 raised to the power 7 and 6.75 into 10 raised to the power 7 Tesla inverse, centimeter inverse respectively, what will be the resonating frequency of carbon 13 at the same magnetic field that is 1.0? See, gamma is, you know, the highest gamma, the highest value of the gyromagnetic ratio is for the hydrogen. That's why it is very, very sensitive. While rest of other nuclei will have the lower value of the gamma, they are not that sensitive. Okay, you should remember this particular point also, which is very important to build your concept actually. How we can solve this kind of the problem? So in that case, again, what I can do, I can solve this problem. Say, you know this from the physical spectroscopy, resonating frequency equals to gyromagnetic ratio gamma multiplied by the magnetic field, external magnetic field, and divided by the 2 pi, right? This is the general expression, right? 2 pi omega equals to gamma b0. From here, from here it is it came. So you have been given two nuclei, H and your carbon. So you can write omega H, which is equals to gamma of H. There is no problem in that, magnetic field, and then you are having the 2 pi. This is the equation number 1, you can say. And then you can write your omega for the carbon. So you can write gamma for the carbon multiplied by the magnetic field divided by the 2 pi. This is the expression number 2. So what you can do, you can divide equation 1 by equation 2. So when you do that, then you will have omega H divided by omega C equals to your this B0 divided by 2 pi divided by this carbon B0 divided by 2 pi. So these two get cancelled and you left with this omega H equals to gamma H, omega C equals to gamma C. Okay, and if you want to put the values here, then it is quite easy. Resonating frequency for this is given as 42.4 megahertz. It is there in the question, guys. You can see here. Where is that? Where is that? 42.4 megahertz. Okay. And then what you will do? You will divide this value by omega C, because you have to calculate for this omega C. 27 into 10 raised the power 7 Tesla inverse. Second inverse is the gyromagnetic ratio for the hydrogen, and 6.75 into 10 raised the power 7 Tesla inverse. Second inverse is the gyromagnetic ratio for this carbon. So these units gets cancelled, and once they gets cancelled, you can rearrange this equation. And if you rearrange this equation, then you will get omega C equals to 6.75 multiplied by 42.4 divided by 27, of course in megahertz. If you solve this thing, then it will give you 10.6 megahertz. So 10.6 is your answer. Let's check. Right. So you can write, you can mark this 10.6 megahertz. So these are the 11. These were the 11 problems from the 2015 examination. I hope you enjoyed the lecture. So if you are watching the video for the first time, please subscribe the tetrahedron chemistry classes. Do share with your friends, because sharing is caring. If you share the video with your friends, they will also learn a lot. Okay, and please don't forget to like the video. We'll meet in the next lecture very soon, which would be your 2016 spectroscopic problem. So that's it for today, guys. Thank you very much.